Okay, ready, go. So our lecture 2 is the gas sensor. Then next page. You could go to read the textbook, the Centuria textbook, chapter 23. Okay, so next page. We have a photo of this gas sensor. We have a filament here, another filament here, and the filament is coated by PT, platinum. It's a catalyst. Then we have a pad. You could see the wire bonding. So this is a voltage controlled sensor. And this filament, inside is polysilicon, and outside it is covered by platinum. Then this gas sensor is for hydrogen gas sensor. If we have hydrogen in the chamber, and the hydrogen will react with oxygen in the air, then the heat due to the combustion will increase the temperature of the filament. This is the concept, but in reality, this system controls the temperature of the filament. Then total heat input to the system. We have the voltage power, joule power, V squared divided by R, into this filament. We also have the combustion, the heat due to combustion, hydrogen plus O2, the heat due to this combustion reaction. So total heat, we have heat from the chemical reaction plus heat from the electrical power. But we want to keep the temperature of the filament constant. Then if we calculate, if we can control the temperature Tm of this filament, then we know the power input from this joule heating. Then we can know the power due to the chemical reaction. If you know the power due to the chemical reaction, you will know the concentration of the hydrogen. So this is the principle of this hydrogen gas sensor. So what's your name again? Okay. So we have a new student, Kumail, from Kashmir. You are from India?
India.
Okay, so you are friends, I guess. Okay, so we have new student. Okay, so you selected this course. And are you a new student? Are you a new student? So are you in this department? Okay. Good. So we have several new students join us. So any question with this hydrogen gas sensor? Okay, so camera, I'm going to ask a question to
A principle of operation. A suitable catalyst, when heated to an appropriate temperature, promotes the oxidation of combustible gases.
Yes, the gas is hydrogen.
Yeah.
Sorry, your name again?
Vipa.
Vipa.
Yes.
Vipa, could you read the second?
The filament is Joule heated to its operating temperature and resistance changes produced by the heat of reaction are detected.
Again, we input the Joule heating power to keep the resistance constant. So by measuring the heat input from the Joule heating, we will know the heat. Because suppose resistance is dependent on temperature. If the resistance is constant, means the temperature is constant. And for this system, temperature is influenced by chemical reaction power plus the voltage input power, V squared divided by R. So if resistance is constant, means temperature is constant. So if you can measure the voltage power, you will know the chemical reaction power. If you know the chemical reaction power, you will know the concentration of hydrogen. Is this clear? Raise your hand if you understand. No one? Resistance depends on temperature. Do you follow me?
Yes.
Okay, so temperature is influenced by heat from chemical reaction and heat from the electrical power input V squared divided by R. And in this system, we control the V squared over R. We can control voltage. If we control voltage, the target is to have constant temperature of our system. If the temperature is constant, then the resistance is constant. So then temperature, we have a meter to measure the temperature. But we say temperature is dependent on resistance. So we measure the resistance. So if the resistance is constant, means the temperature is constant. So temperature, let's say resistance now is influenced by chemical reaction power because heat generation due to this chemical reaction and heat due to the Joule heating. So temperature depends on chemical reaction heat and Joule heat. If you follow me, raise your hand. Okay. Now, if the resistance is constant, means temperature is constant. Because we use the voltage V squared over R to control the resistance. So now the resistance is constant. But the resistance depends on chemical power and Joule heat. So because V squared over R, we know it, we control the voltage. So we control the voltage to get constant resistance. Then we will know the amount of chemical power because C equal to, okay, R, let's say R equal to chemical power plus electrical power. If you know the amount of electrical power, because resistance R is constant, so we can calculate the amount of heat due to chemical reaction. if you know the heat due to chemical reaction, you will know the amount of hydrogen. Okay, raise your hand if you understand. Okay, so we will have 5 minutes discussion time. You need to record the discussion due to so raise your hand if you understand. Again, raise your hand. 1, 2, 3, 4, 5. Okay, so you three is a group. And Frank, Borton. So U4 students is another group, and U3 is another group. We have group 1, 2, 3. So we have 5 minutes discussion time. If you don't understand, please discuss with your fellow classmate. Okay, so, okay, start. Because temperature is not easy to control, so they, other than control the temperature, control the resistance, because temperature depends on resistance. So if you control resistance, means you control the temperature. Okay, so Abi, could you read the third one?
Therefore, control resistance and measure the power needed to maintain that resistance value.
Yes, so the power is V squared divided by R, the power input. Ahwan, could you read the fourth?
And entering the resistor from one head of reaction to Joule heading.
Yeah, the heat, we have two sources. Source 1 is the heat of the reaction, the chemical reaction. And source 2 is the Joule heating from the electricity, voltage. So if you can calculate the Joule heating power, because imagine at the beginning we keep the temperature to 500 degrees C. We just use the electricity power input. Now there's no chemical reaction. So say now voltage is say 10 volt. 10 volt input voltage to keep the chamber temperature 500 degrees C. Okay, now we put our sensor into another surrounding, another environment with hydrogen. Okay, now the hydrogen react with the air, oxygen, to produce heat. So remember, now we need to decrease the voltage in order to keep the temperature at 500 degrees C. So you decrease the voltage. So from the amount of the decrease in voltage, you can measure the amount of hydrogen inside the chamber. Do you get it? Okay. So in this is the schematic. We have the filament, polysilicon filament, coated with platinum. And the input is the gas. So we want to know the concentration of the hydrogen in gas. And the ambient, we have air, means we have oxygen. So we have this filament. But we need to have the electrical engineer to design the resistance control circuit. Means we need to measure the resistance. Then based on the resistance, we control the voltage. So the circuit need to measure the resistor value. Then we need to compute the power we need, the voltage. So this is the work of mechanical engineer. This is the work of electrical engineer. So that's why electrical engineer has more work to do. You have 2 blocks to play. And mechanical engineer only have this tiny block to play. Okay, so next page. But to design the system, we have mechanical subsystem, electrical subsystem. Then for the system modeling, we too have a simple model to tell the designer what to do. Okay. Agan, previous. Agan, read this, please. Okay, previous. Yeah, previous. Previous. See, we have this filament, anchor. We want to have the model for this filament temperature distribution. So we assume anchor and anchor, let's say 0 degree C. So all heat would go, the heat in the filament will go to the sink. This is the only way for the heat to go. We assume in reality, heat can have interaction with the air, and heat can have interaction with the substrate. So heat, substrate, heat conduction, heat, air, heat convection. But to simplify the model, we start by assuming there's only heat conduction to the anchor. Next. Bottom, read this, please.
Assumed heat conduction down the region of the filament is the only bit those localities.
Yes, we assume heat can only go to the 2 ends, the 2 anchors. Frank, could you read this? See, the filament is long, and in reality, the temperature at each point of the filament is different. The resistivity of silicon depends on the temperature. So in reality, the resistivity at each point of the filament is different. But now we assume the heat generation at each point is the same. In reality, the heat generated in each point of the filament is different. But we assume it is the same. So what's the name for your name? Stephen. Please read this. Yes. We assume the material properties, say kappa, the heat conduction is constant at each point and depends on, it won't be influenced by the temperature. Actually, kappa depends on temperature too. So, but now we assume kappa, heat conductivity, is a constant to simplify our model. And sorry, raise your hand if you are electrical engineers. 1, 2, 3, 4. And raise your hand if you are a mechanical engineer. Mechanical. 1, 2, 3. Okay. And so you are optical engineer. Material. Chemical. So what was your major?
Precision.
Precision.
Precision engineering.
Precision. But I mean, what was your major in college? Chemical, civil, material.
No.
Electrical machinery. Okay. So what was your major? Precision. In college, university. Mechanical. Okay. All right. So this is the heat conduction. The equation T represents the temperature of the filament. Depends on the location, x coordinate. And I is the current flow in the filament. Rho E is the resistivity of the filament. W is the width of the filament. H is the thickness of the filament. Kappa is the thermal conductivity of the filament. You don't need to worry about how we got this equation. This is the job of the mechanical engineer. Then, to solve this partial differential equation with boundary conditions, remember the two ends. The temperature is the anchor temperature. So we can solve this partial differential equation with the boundary conditions. We will get the result. We assume x from x minus L over 2 to L over 2. L is the length of the filament. Okay, next page. So this is a solution of the partial differential equation. If you learned engineering mathematics, you should also have the technique to get this solution. So T0 is the anchor temperature, the substrate temperature. And Tm is the maximum temperature. You can do, okay. So if you are a mechanical engineer, you should learn how to get the solution. If you are an electrical engineer, you don't need to worry about this. Okay, next page. Sorry, what's your name? Yes. Leo. Leo, could you read this?
All metals and silicon are temperatures were lower than that at which is conductivity is demanded by intrinsic carriers have positive temperature coefficients.
Yes, thank you. Say, below the threshold temperature, the metal and silicon, their conductivity has positive temperature coefficient, means temperature increase, conductivity increase. So this is positive temperature coefficients. If temperature increase, conductivity increase, means the resistivity decrease. Okay, so this is the reason we use voltage control other than current control. say the dual heating, if you use voltage control, let's say if you use current control, the dual heating power is I squared times R. So because I squared times R equal to I squared times electrical conductivity. I squared divided by electrical conductivity. Then if we want to use current control to heat the filament, we increase I, and we have the power input, the heating power. But remember, conductivity increase if temperature increase. So now I squared divided by conductivity, electrical conductivity. Now electrical conductivity increase means the power input decrease. If the power input decrease, you need to keep increasing the I current. Then remember, input I, power input, temperature increase. But temperature increase, conductivity increase. Conductivity increase, the current power decrease. Current power decrease, you need to increase the current again. So you just keep going, keep going. The system will go unstable. The system will lose stability. But if you use voltage control, V squared divided by R. So V increase, power increase, temperature increase. But temperature increase, conductivity increase, resistivity decrease. If resistivity decrease, then the power will increase. You don't need to increase voltage to keep the power input at certain level. So this way, the system will be stable. Raise your hand if you understand. Good. Let's have, again, 5 minutes discussion time. And try to figure out this. Take some time to discuss within your group. The dual heat is V squared divided by R. But R equal to rho EL divided by cross-sectional area. The cross-sectional area is W times H. So this is the total dual heat. So if the rho E resistivity is low, you can get high dual heat. High dual heat means high temperature of the filament. Okay, next page. Then we want to calculate the resistance of the filament. So, but remember, now the temperature increase due to the dual heat. So suppose this is strain, this is original length, this is length increase. So length increase divided by original length is the strain. Then the new length equal original length plus length increase. then length increase equal to strain times L. So you can move L out, then 1 plus epsilon. But now, the strain, because remember temperature increase means thermal expansion. So the strain due to thermal expansion is coefficient of thermal expansion times temperature increase. So now we have a length. This is the filament length. We select one tiny section. The length is dx. So the new length dx prime equal to original length dx. We select this segment dx. So now we have the new length due to temperature increase equal to dx times 1 plus epsilon. Epsilon now is temperature, thermal strain equal to alpha delta T. So delta T equal to current temperature times minus original temperature. But we take T0 equal 0. We use 0 as the initial temperature. So epsilon T now equal to alpha T. So now we put alpha T here. dx times 1 plus alpha T is the new length of this segment dx. And R so R R equal to rho E dx prime divided by WH dr. So remember we have length, total length L. We have tiny segment dx. And the resistance dr due to the dx is rho dx divided by WH is dr. So total R equal to integration dr equal to integration rho E dx prime. dx prime equal to 1 plus alpha T times dx. Then WH but WH is a constant, so we can move, and we assume rho E is constant. So we assume rho is a constant. Rho WH integration x from minus L over 2 to L over 2. 1 plus alpha T dx. So we can get this WH rule. WH, if you move rule outside, you are left with 1 plus alpha t dx integration minus L over 2 to L over 2. Okay? If you don't understand, raise your hand. Okay? Now, we assume, okay. What's your name? Leo, and what's your name? Ethan. Ethan, could you read this?
Alpha R is the temperature composition of the resistance for the filament material to be a constant over the temperature range of interest.
Okay. So if this is a constant, this is a constant, then we can do integration to derive, but T temperature depends on the dx previous. See, T is a function of x. And we take T0 equals 0. So you replace T of x using this expression. Next page. Next page. You put T using that expression and do the integration to reach this one. Okay, now everyone, can you try to find an A4 paper? If you don't have A4 paper, TA, could you go to our room to take the script? Yeah, if you don't, yeah, everyone get a square paper. Write down your name, your student ID. Then start from this equation and using that equation to derive this equation. Okay? Write down your name and student ID. Sorry, everyone. So in the textbook, this alpha is not coefficient of thermal expansion. It's the coefficient of this resistivity. So the resistivity, it depends on the temperature, and this is the coefficient. In this case, the length does not depend on the temperature. So there's no thermal expansion. So this alpha is for this resistivity. This resistivity depends on the temperature. To correct. Okay, please do the derivation. Write down your name, your student ID. You can discuss with your classmates.
S 像在那边对吧？啊不，对，小的那边
对啊，就是先不看，再再聊。对对。
对啊，
那边这样包括对，因为那个是
应该不会。那个。
For gas sensor, it's important to know the response time. We cannot take all day long to wait for the gas sensor to tell us the result. So the response time is very important for the sensor. But for this thermal system, in order to estimate the time constant of the system, we need to know the R value and C value, because time constant equal to R times C. But here it's a thermal system. So R in electrical system, time constant may be calculated by resistance times capacitance, time constant. But for thermal system, we need to calculate the thermal resistance and the thermal capacitance in order to know the response time of this thermal system. Please, your name? Huh? Even? Steven. Steven, please read this one. Okay. See, eigenmode, previous. So for this PDE, partial differential equation, we have many solutions. We have, say, eigenmode 1 solution, eigenmode 2 solution, eigenmode 3 selection, because it's a partial differential equation. Think about the Fourier X series. A function can be expressed by a Fourier X series with infinite sine and cosine terms. So for the fundamental mode, in order to simplify the problem, we just take the mode 1 solution, eigenmode 1, to get the solution. Easier for us to take the intuition to have the relation between solution and because eigenmode 1 is the simplest solution. So we just select that one. Okay, next. Okay, so we select the lowest, means the first one, the first eigenmode solution, to estimate the time constant. Frank, could you read the second one?
That the temperature profile has been established and find the decay constant when the GOPT is turned on.
Yes. So first, we turn on the voltage, the source. Then the filament is heating. Then we have a temperature profile of the filament. Now we turn off the voltage power source. Then the temperature will decrease. So this is what we do. We turn off the dual heating, and we observe the temperature drops to calculate the time constant. Even, are you even? Evan, sorry. Ethan, please read this one.
operating temperature profile is a superposition of many atoms. Each having its own decay constant. However, to get a raw estimate, we can use the lowest eigenmode and solve the time-dependent heat flow equation with no actual heating.
Yes. So we turn off the voltage source, so no dual heating. Then we select the lowest eigenmode to estimate the time constant. Because each eigenmode has its own time constant, but we select the fundamental mode. If you want to get accurate solution, you need to consider many eigenmodes, but we don't do that here. Next page. Okay, so this is the temperature distribution as a function of position x and function of time t. So this is a typical heat transfer equation. So you can think this one is heat running away. You can think, okay, kappa times partial second differentiation with x. So this term is heat conduction. This is heat source, capacitance. So if I have heat and my heat running away, so you can think this is the heat source. This is heat running away. Energy balance. So you can think this one, energy decrease, but energy must have some place to go. So energy go away through heat conduction. This is what I mean by energy balance. Do you understand? If you don't understand, raise your hand. Okay. You drink water, but water must go somewhere. Either you go to the restroom to pee, or you run and you produce sweat. The same for thermal energy. C tilde is the thermal container. If the thermal energy decrease, it must go somewhere. So it can go through the heat conduction to transfer to the other part. Okay, so C tilde is the heat capacity per unit volume. Then remember, we select the lowest mode, eigenmode. So we try this solution, cosine pi x divided by L, e to t minus time constant. Tm is the maximum temperature. If you do 2 pi mod 2, 3 pi mod 3, or 5 pi, 7 pi, you can have many mod 1, mod 2, mod 3. You add all the modes together to produce the final solution. Then the solution is very accurate, but it's too complicated. So we just select the mod 1 as the solution to approximate, to estimate the time constant. So tau is the time constant. Then you can plug the solution into this PDE, then you can get this time constant. C tilde L squared divided by pi squared, kappa. Okay, so Amin, please read this one.
Create a very low first order dynamic model of the filament if we treat this time constant as the product of the thermal resistance and the longitude capacitance. The two appropriate quantities are
Okay, so this is time constant. So time constant equal resistance times capacitance. So we have the thermal resistance and capacitance is a lumped capacitance. So time constant equal to thermal resistance multiplied by capacitance. So RTH times CTH must the same as time constant, this one. So C8 cancel out, WH cancel out. And you have L square, CTO dot, pi square, kappa. So yeah, if you multiply these two terms, you will get this time constant. So, but we won't go to this mechanical derivation of each terms. We just take the result as it is. Then the unit for thermal resistance is Kelvin per watt. And the unit for capacitance is joules per Kelvin. Then if you times Kelvin per watt times joules per Kelvin, if you do the calculation, Kelvin per watt is times joules per Kelvin. So Kelvin cancel out, and watt is joule per second. So joule cancel out, move second to the denominator, you can get second. So second is the unit for time constant, second. So this is accurate in terms of the unit. Ahwan, do you understand? Okay, next page. Okay, so our estimation. So this is temperature increase. You can move this CTH to so this is heat capacitance times temperature increase. So this term is the power. So this is power. So power either come to the voltage power, your power source, voltage source. V squared divided R, your power to the filament, or the PC, chemical reaction power. So chemical reaction power can increase the power of the filament, or power source to increase the power. And this one is the if you don't have power input, then this one temperature will decrease. So this is a time constant. If there's no input, then you can use this equation to know this is time constant. Because we have time constant, temperature decay. So you need to have this term to represent the temperature decay. Steven, could you read this and this and this? Yes, so PC is the heat of reaction. And this one is the voltage control term, power input. Agan, yeah, please read this.
Since there is vector link between Tn and the temporal systems, we expect that access to first order control of resistance will serve to control Tn.
Yes, see, the resistance of filament depends on the temperature, Tn. So if you control the resistance, means you control the temperature, Tn. Okay, what time is it? 3:47. Okay, let's continue. Okay, next page. Now, we have this equation. It's just an equation. We cannot get too much just from the equation. We need to solve the equation. We can use MATLAB Simulink to solve this equation, to get information to help us to design our gas sensor. So look at this is Simulink model using MATLAB. So Tn, the temperature. So temperature output, temperature. So this is Tn. But Tn, this is differentiation. So we have V squared divided by R. Here we have, so voltage. So this is filament. We have voltage and PC. PC comes here, voltage here. And so this function, input is voltage, and PC, input. We have three output. Output is temperature, Tn, and the resistance R, and the result, V squared divided by R. So this is a monitor to show this power, monitor to show the temperature, and the monitor to show the voltage. And PC, we have a monitor to show PC value. And the PC input, so this is the source. This is source. So this PC source get in. And this is the, we want to set the resistance value. So this is the resistance, we set the value. So this is the monitor to monitor the resistance value, set point resistance. And this one is the resistance from the system. So the resistance from the system, this is the monitor, comes to this. So this one is error comparison. We compare the set resistance with the real resistance. Then this is our controller. It could be P controller, PI controller, or PID controller. You can select your controller. Here is just a proportional controller. So we use a controller to get the voltage signal. We input the voltage to our plant. This is our plant. And PC input to our plant. So this is our plant equation. The whole plant could be represented by this equation. So we have you can think this is a subsystem. This is our system. This is the subsystem. So this subsystem in Simulink, this is the content of the subsystem. So remember, this is Tm, and Tm integrator if you so this is the relation R as a function of temperature. So you should get this from manual, R as a function of temperature. So Tm input, R output, input, output. Then this is a multiplexer. You have two input. You have voltage and resistance. And because voltage V squared divided by R is a joule heat. So this is a calculator to calculate. So this is multiplexer. We have U1, U2. So, okay, U2, this one. U2 squared, voltage squared divided by U1. U1 is R. So V squared divided by R is the joule heat. So this is the joule heat monitor, 3. This one is 3. And 1 is RTM. So 1, 2, 3. So output 1, output 2, output 2 here. This is output 2, output 3, output 3 here. This is input 1. Input 1 is this one, input 2. So input 1 and input 2. So you need to look into the direction of the arrow. So this is get into the system, input. This is get out of system, output. So plus, plus, minus. Plus PC plus V squared divided by R. This is V squared divided by R. And minus this one, T divided by R. Then C divided by C times 1 over C is divided by C. So, but this one here is Tm dot. Tm dot integration equal Tm. So this is integrator. And Tm get in, and this calculator will give you the R, because R equal to R0, 1 plus 2 over 3 times TCR divided by U1. U1 is the input. So this is the filament subsystem. This one, this one. Any question? Do you have experience in Simulink? Raise your hand if you used Simulink in the past. That's good. You? Okay, good. So have you ever used the subsystem? You use this one. So good. Next page. The controller, previous page. So this is the controller. Okay, next page. So the controller, the arrow, see, we have plus, minus, so the arrow gets in. This is KP controller, proportional control, 1.6. This is saturation. The output will saturate it at certain value. Otherwise, you will get voltage output. So this is the Simulink model for our system. So next week, we are going to do the Simulink modeling. Okay, so any comment today? Any question? Okay. So I'll see you next week.